But up next, Kyeongmin is going to tell us about detectable recoverability and persistent memory. Please take it away.
Okay, thank you for the introduction. Today I'm going to talk about Memento, a new framework for persistent memory programming. I'm Kyeongmin Jo, and this is joint work with my wonderful colleagues Seungmin, Azalea, and Jeehoon. Let's start with understanding persistent memory. Persistent memory is an emerging storage technology under development by industry giants like Samsung and Kioxia. Like SSD, it's non-volatile, but with better latency and throughput. Interestingly, it allows byte-addressable access similar to DRAM. The ability to access non-volatile data like DRAM has inspired various performance-enhancing data structures for persistent memory. However, designing for it is difficult due to system crashes. A crash during a data modification can lead to inconsistency in persistent memory. Incorrect recovery can result in data loss. So, understanding how to design crash-consistent data structures becomes essential. But first, let's clarify, what does crash-consistent really mean? A widely used correctness criterion for this is durable linearizability. It ensures if a function returned before a crash, its effect is durable. For instance, consider a banking example with a durably linearizable function withdrawing $100 from my account. That has $150 stored in the persistent memory. After we execute this function, my balance drops to $50. The function returns true, stored in volatile memory such as cache or DRAM. If a crash happens, volatile memory disappears. But after a recovery algorithm restores data structures, $50 stays in persistent memory. Thanks to durable linearizability, the withdrawal effect remains after crash. However, durable linearizability isn't always recoverable when composing multiple data structures. For instance, let's assume that a code was added to deposit the withdrawn money into Seungmin's account. Starting with reducing my account to $50, then a crash occurs. Following the crash, the recovery starts. But it only knows my balance is $50, lacking the transfer's context. So the $100 disappears. For reliable programming through simple composition, we need a stronger correctness criterion. That brings us to a stronger correctness criterion known as detectability. Detectability extends durable linearizability, ensuring we know if an operation completed. With each function detectable, after a crash, when the recovery code is executed, it recognizes the withdrawal function was completed. With this information at hand, it may decide to complete or roll back the transfer. So, detectability enables the recovery of a simple composition. Then how do we design detectable data structures? There are two objectives we need to keep in mind for design method: easy to use and performance. Some methods have high performance, but require manual data structure crafting. Others are easy, but have performance issues due to overhead. So our dream is to devise a method to satisfy both of these goals. Our solution is the Memento framework, which is both easy to use and highly performant. Memento presents a type system that guides to design detectable programs and lightweight building blocks. And our underlying principle is replay. Specifically, our key idea is to achieve detectability by replay. After a crash, we simply rerun the program and recreate the pre-crash context. Detectability, or knowing the extent of operation execution pre-crash, is ensured by fully restoring the pre-crash context. Let's return to our example. Detectable data structures may run recovery code after a crash, but in Memento, no need for recovery code. We just replay the program. We restart from the very beginning. Now, let's see Memento's recovery. We start with the detectable withdrawal function. Memento understands this is post-crash execution, so it skips the actual withdrawal and returns the pre-crash value true. Now, Memento has fully restored the pre-crash context. Following this, it simply continues the program to deposit $100 into Seungmin's account. In summary, Memento replays the program until the crash point and continues the program. Then how do we know if it's safe to replay the program? This is done by our type system. Our type system statically ensures successful deterministic replay, and we have proven this. Then, what makes our type system special? Let's take a look. In this talk, I'd like to introduce 4 core rules. I'll explain each rule using the withdrawal function as our learning example. Rule 0, our foundation, is the Memento descriptor. Placed as the function's last parameter, the Memento records progress and result in persistent memory. During the withdrawal function, the balance drops, and the function completion and the return value are recorded in the Memento in a logically atomic manner. After returning true, if a crash occurs, Memento restarts the program, beginning with the withdrawal function. Then it checks the Memento descriptor, skips the actual withdrawal, and returns the previous value. Finally, the success variable becomes true again. So, Memento ensures the same volatile value is always obtained when replaying, even after a crash. How is this possible? Let's explore the detectable withdrawal's internal implementation. But before that, consider the pure lock-free version of withdrawal function, unconcerned with detectability, which may look something like this. It firstly lists the source balance, then compares it to amount. If the balance is not sufficient, it cannot withdraw and returns false. Finally, it subtracts amount from source. It uses a basic concurrent primitive operation, compare and swap, to perform the subtraction only when the status of source is equal to the local current variable. If successful, it returns true. Otherwise, it repeats the process. Then, let's make this function capable of replay. There are some challenges to replay and corresponding rules to overcome it. The first challenge lies in the non-deterministic load result. Post-crash value may differ from the pre-crash one. In detail, assuming source balance is $150 and amount is $100, loading source returns $150. Because the balance is sufficient, KAIST is performed, successfully executed, decreasing source balance to $50 and returning OK. Here, just before returning true, a crash happens. The program restarts and loads source again, but load now returns $50, different from the previous value, going to the wrong branch. When the return value of load changes like this, the control flow also changes and replay isn't correctly performed. We address this by providing the checkpoint primitive. Rule 1 says that read-only blocks like the load function should be wrapped in a checkpoint primitive. Let's delve into this. It takes the read-only function and Memento as parameters and returns the function's result. By executing the read-only function and recording the outcome, it keeps the lead value for retrieval after a crash. Now let's apply rule 1 with the checkpoint primitive to the withdrawal function. First, when checkpoint runs, loading source is actually executed. Its return value $150 is stored in the checkpoint Memento. The value is returned, balance is sufficient, so KAIST is performed, just like before, source is reduced. A crash happens and the program restarts. The checkpoint Memento doesn't load source again and skips it. Knowing the return value is $150, it retrieves and returns the value. As the current variable is correctly restored, the control flow follows the previous path. Thanks to the checkpoint, the lead value is preserved and the subsequent control flow correctly replayed. But we are not done. There's another challenge. Next is the undetectable KAIST challenge. If source is currently $150, KAIST succeeds. But because KAIST already succeeded before the crash, we end up double withdrawing. So the plain undetectable KAIST means we cannot replay correctly. To solve this problem, we introduce a primitive functioning as a detectable KAIST. Rule 2 mandates using detectable KAIST in place of plain KAIST. As a Memento function, detectable KAIST takes an additional Memento parameter and ensures replay. Moreover, it executes the compare and sub operation only once across crashes. Then let's learn the code where KAIST is replaced with detectable KAIST. We assume that the earlier part executed the same as before, and the completion and return value OK are recorded after executing the detectable KAIST. Then a crash occurs. When it is executed again from the beginning, the checkpoint's replay returns $150, then CAS is run. With the pre-crash context stored in the Memento, it skips the compare and swap and retrieves the return value. In the end, OK is again returned. Also, because it did not actually perform the compare and swap, the fact that the compare and swap was performed exactly once is maintained. But still, there is a challenge. So far, we've checked Memento for replay. But what happens when we are dealing with loops? For instance, let's suppose that the compare and swap fails. So we loop again, but should the Memento replay? If so, it'll lead to an infinite loop. So while looping a Memento function, we must be able to continue executing by distinguishing each iteration. To correctly distinguish iterations, our solution is to use timestamp. Actually, the completion check is a timestamp. What this means is Memento primitives, such as checkpoint or detectable CAS, record the timestamp on completion. This lets us know not only if, but when a primitive was executed. Using the timestamp, we accurately distinguish iterations by conducting replay only when the Memento's timestamp increments. Starting from the beginning, our Mementos initially have a timestamp of 0. When a checkpoint and failed CAS completes, it records the current timestamp, let's say 10 and 20. On looping again and checking the checkpoint's timestamp, it's found to be less than 20, the previous CAS's completion timestamp. So this is not a replay context, and the load function is not skipped. When the checkpoint runs again, it overrides the new execution data into the Memento. After a crash, the checkpoint is replayed, but CAS is not, because the CAS Memento's timestamp is smaller than the last Memento's 30. So this CAS is actually executed. In summary, using timestamp allows us precise inference of crash points for accurate program replay and continuation. In fact, rule 3 related to loop is simply use the loop. Now let's continue from where true is returned. The detectable withdrawal function, using its internal Memento primitives, checkpoint and detectable CAS, inherently keeps track of the fact that true was returned at timestamp 40 without needing to physically record this information itself. Similarly, the detectable deposit function may complete at timestamp 60. So we can consider that the transfer function also completes at this point. We easily get a new replayed function through simple composition. In this way, a detectable high-level application can be composed from the bottom up. To show the overall performance, we evaluate the fundamental primitive detectable CAS and a Memento-based composed linked list. First, here is the Memento's detectable CAS evaluation. We compared Memento CAS with existing detectable CAS operations. The results showed that Memento CAS has high throughput in both high and low contention. Also, we measured how much memory CAS uses for detectability. As can be seen from the graph, Memento CAS shows minimal increase in space overhead, even as thread numbers increase. Next is the evaluation of a composed linked list. We compared Memento linked list with detectable linked list derived from existing detectability design methods. Within a range of 20 keys, the Memento list exhibits high performance in both measurements. On the other hand, within a range of 2,000 keys, the Memento list is comparably fast with competitors. So far, I have explained the core concept and experimental results of the Memento framework. The paper includes the other things not mentioned in this talk, such as implementation of primitives and test or model checking for correctness. Please refer to the paper if you're interested. Also, Memento is open source on GitHub. Thank you for your attention.
Great talk. So just to remind everybody, we got the mic up here at the center. And for folks watching on the stream, please put questions in the Discord.
Hi, Shripati Pai, University of Rochester. So I had a couple of questions. A clarification question first. The persistent memory device you're using, is that byte addressable or is this block persistence?
Would you please say it
So
again?
what is the device, persistent memory device you're targeting this to? Are you targeting byte addressable devices like Intel Optane? Or are you targeting flash memory devices which are usually block?
Yeah. Like Intel Optane.
So your evaluation was done on the Intel Optane?
Yeah.
Okay, so the Intel Optane is dead in some sense. But if you consider the standard consistency models, usually no linearizability is not composable. So you usually go to serializability with transactions. So have you compared your work against, serializability with transactions for performance differences?
Yeah, that is a good question. Also, we think the transaction is can be an alternative, but in our evaluation, the transaction is very slow to use compared to our Memento-based composed data structures, and also transaction system usually have its own concurrency control mechanism, and each rock-free data structure has its own one too. So combining the two different mechanisms is not straightforward, I think.
I see. Thank you.
Yeah.
Hi, thanks for the talk. Rupanshu from Stanford. If I understand correctly, if I want to use Memento for my program, I will have to change a lot of lines of code to add the checkpoint primitive and so on. Is there any way to automatically do that without the user having to change the program in lots of places?
So your question is that is there any automatic mechanism? So yeah, this is a good question, which means I already prepared the answer. So this is also future work in the Rust bullet. We prepare automation, plan to leverage automation techniques, possibly developing a compiler to automate Memento type checking. And you are not done at this
thank
point.
you.
Yeah.
John Shalmish. So if I understand correctly, after a crash, you need to rerun the entire program from the start. And I'm just wondering, if you have a long-running server, for example, that's been running several months, are you really going to rerun it from the start after a crash?
Would you please say slow it again? Sorry.
Yes, if I understood correctly, then after a crash, you have to rerun the entire program from the start. And I'm wondering about long-running programs, like servers that might run for several months, for example. Do you really have to restart them from the very beginning? Maybe repeat months of computation?
So your concern is that replay may be too long, right?
Yes, if you have a long-running program and you must restart from the beginning, then replay may be very long.
So the answer is that I understand your concern about potential performance degradation due to replay after a crash. However, it's crucial to remember a few points. Firstly, crashes are relatively infrequent events. Most of the time, the system runs without any issues, so the necessity for replay is not constant but an exception. And secondly, even when a crash does occur, the replay time is not wrong because we optimized the process using a timestamp system that allows to go directly to the last iteration or loop, effectively skipping our iteration before.
I see. Thank you.
So I think we're going to go ahead and do the switch over. I'm so sorry, but if you pop your question in the Discord, we will make sure that somebody covers it. Yeah, thanks. Let's thank Kyeongmin again.